Yeah, what's today's purpose?
We'll see how small forces from one wave will result in a really big wave.
And Brandon, relevance.
This is how opera singers break glass.
You may have seen a cartoon where an opera singer breaks a glass, or a cartoonish movie, but it really can happen. Success. Grant.
I will make a resonance wave.
That's a lie. You won't do that. Today's grades. You're going to get a grade for the resonance lab. Again, you're just going to show me. You're not going to submit anything to the computer. Next quiz is Monday. Next class. Okay, now, when we look at this little simulation, we're going to have red waves start off on the line. That represents the incoming wave that's going down the length of one of these slinkies, and it hits a firmly anchored end. And then it's going to bounce back. Now, the red waves are going to continue going to the right, but the bouncing, reflecting waves are going to be colored blue, and they're going to be on the bottom side. So you have red on the top going to the right, blue on the bottom going left, kind of. At least that's how it starts off. But the blue reflected waves are going to interact with the incoming red waves, and the result is going to be the black line. The black line is actually what the slinky is going to look like when all of these waves interfere with each other. Okay, so let's go to that right now. Oh, France, where is it? I lost it. There we go. This is it.
Alright, we'll now have a look at how we can form a standing wave by disturbing a string so that a continuous traveling wave travels towards a fixed boundary and reflects and interferes with itself, really. So the reflected wave interferes with the wave that's still in on the boundary. Let's have a look at what that looks like. So here we can see we're creating a continuous up and down disturbance on the left end of the string, which causes a continuous traveling wave, which is the red wave here, to travel towards this boundary. And so this wave is represented by the red wave. What we're going to do, what's going to happen at the boundary is we're going to get an inversion of the wave and reflection. We're going to have that represented by a blue wave traveling back in the opposite direction. So I'll just slow this down while it's happening. So here we can see that the first wave, part of the wave, is just about to arrive at the boundary, and it reflects and inverts, and the reflected wave interferes with the incident wave that's still arriving at the boundary. And that interference results in a kind of cancellation of parts of the wave, so they're interfering as per the principle of superposition. And we'll just speed the animation up again. And what we can see is that the returning wave, the reflected wave, interferes with the incident wave. We have the conditions required for a standing wave to be set up. And you can see that we get this pattern of stationary nodes and antinodes along the wave, and we have a standing wave, which is this black wave.
So the red waves appear to be going to the right, and they are. The blue waves are going to the left. The crests, the humps, are moving in those directions, right and left. However, the humps of the actual slinky that would actually see, they're growing bigger and smaller, but the humps themselves are not moving to the left or to the right.
Which is just the superposition of the two waves of equal amplitude and equal frequency traveling in opposite directions. And because of the phase change that happens at the boundary, we always end up with a node at the fixed boundary. Okay,
now notice here, when the two humps are together, they add to be a giant slinky hump right there.
That's a boundary condition for a standing.
At this moment, the red and the blue are opposites each other. Go away, add, go away. And so they cancel out, and the actual slinky is going to be all flat. Okay, let's go to our notes. Number one, the first important background fact. When waves reflect, let's get big again. There we go. First important background fact, when waves reflect or bounce off of a fixed end, they bounce on the opposite side. Second important background fact: when waves interfere with each other, they sometimes add, they sometimes subtract. Sometimes a wave interferes with its reflection to make a standing wave. The places, this kind of wave does not appear to move right or left, it just stands there and wiggles. The place where they sit at the axis are called nodes. These are the places that don't really wiggle at all, they just sit there. There will always be nodes at the two ends of the standing wave. There are usually nodes in between the ends as well. The places that wiggle the most are called antinodes. Only certain frequencies will bounce back to interfere with incoming waves correctly to set up a standing wave. These frequencies are known as resonant frequencies. Now, since the slinky has a certain tightness, it's going to have a certain speed, a certain velocity of waves going through it. It doesn't matter how hard you shake it, how fast you shake it, the waves are going to move at the exact same velocity. We had the equation V equals F lambda. So we're going to give, it always has the same velocity. Only certain frequencies are going to have this standing wave. So only certain Fs are going to be allowed in this situation. And so therefore only certain wavelengths are going to be allowed. And so these frequencies or wavelengths allow full waves or half waves to fit perfectly between the endpoints. So if you want to figure out how fast you have to shake or how long the wavelength is going to be that's going to be a standing wave on a slinky, you measure its length, and you can do this mathematics in order to figure out the frequency that you need to jiggle it at. So to help understand that, you want to have, here's a black line that is a slinky or a rope or whatever you have for the medium. And then the O's here, the zeros, represent the anchors where they are connected to some kind of a solid point. We could have a standing wave where just a half a wavelength is between those two, and that just wiggles back and forth, up and down. This point right here goes back and forth, back and forth. Or we could have one full wave be a standing wave. Notice here there's a little gap. That's where the line is going to go through. You could have a standing wave there. This spot right here stays in place. The two ends stay in place. They're anchored. But this spot here is just going to go back and forth a lot. This point here will go back and forth a lot. This point here will go back and forth less. Okay, then we could do this. Again, the little gap is where the line goes through. So there you have three humps that will just wiggle back and forth. And these two spots are called nodes. They will not wiggle at all. You can go ahead and do the other two on your own right now. This can happen with any kind of a wave where you can anchor things down in one way or the other. Here's a video about a big water tank, and they have a standing wave. You can't anchor water down, but you could have it splash against a solid wall. It's sort of like anchoring it. So let's see here. Click on that, click on this, back on that. Second video. Here we go. These waves do not appear to be going from one end of the tank to the other. They appear to just be going up and down in one spot. these waves are moving. You can tell that, coming towards us. But when they reflect, they start to interact with the reflections, and a standing wave will develop. And now, there we go. Okay, next. Where are we at? No. Oh, the bridge. Close that down. Back up. Okay, now then, probably the most famous video shown to just about every physics student in the entire country. The Tacoma Narrows Bridge collapse. This was in the Northwest, I think Oregon, maybe Washington State, and it was a nice big suspension bridge built in the 30s. And it was in a valley, and the winds, when they were just, right around the 30-mile-an-hour mark, 30 to 40s, it would be pushing on the bridge, and the bridge would wiggle a little bit. And so it got the nickname the Galloping Gertie. And one day the winds were going down the valley at just the right way, like 42 miles an hour, consistently. And that caused this resonant frequency and caused things to start to vibrate a lot, like we just saw with that water in the tank. The initial waves you could see were rather small, but when they got the standing wave, it got to be really big. Same thing with this bridge. There was one car that stalled out because of the severe shaking, and the guy got out and escaped all right, but then he realized, my dog is still there, and so he walked out and he got the dog. And you can see that he's walking back right in the middle, right on the dotted line of the road, because that was in between the swaying back and forth. That was the one place that he wouldn't get literally thrown up into the air because of this twisting motion. And he got out okay. Uh-oh, rats, what happened? Oh, sadness. Okay, I gotta go to YouTube then and do it that way. This is steel and concrete twisting like that. That is not sped up either. That's how it was looking. Hard to see the car, it's right there. Oh, there's the car. see him walking there in the middle of the road, so he's most stable there. He's having a hard time keeping his balance, so you can see him wandering from one side to the other. They missed the first couple seconds of the falling, but here is the rest of it. Let's see that again. Okay, enough of that funness. Okay, next. Watch the teacher demonstrate standing waves with a snaky. Lay them unstretched on the lab tables with the wall end anchored. You will send wave pulses down at the given frequencies. Use the online generator to set it up. Okay, now, I need somebody to help me out. Okay, Grant, come on down. You're going to type in these frequencies. Online, come on, generator. You're going to start off with 1.3 here, and then you're going to type in the other numbers, 1.85, etc.
Don't you have to start with 0.7?
Nope.
When do I switch it?
When I tell you. Oh, I don't hear anything.
Because mine's not.
There we go.
Oh, God.
Okay, looking back here. We have, Grant, go ahead, type in the 0.7. If I just send a single wave pulse down, you can see the wave move down towards the wall and bounce back. The hump is actually moving. However, if I do it at the pace that the clicker is doing, okay, now the wave is not appearing to go left or right, forward or back. It's just simply wiggling one way towards Lily and then back again. Okay, go ahead and do the 1.3. Okay, this spot in the middle is not moving much at all. This spot here is moving about 2.5 feet. This hump is just going up and down. It's not really going down the path. Go ahead, next one. No. There you go.
It doesn't type in 1.85. It doesn't like straight words.
Try using the, okay, there you go. Try using the other digits, the numbers on the top of the letters rather than the number key, the keypad. There you go. Again, right here is a node. It's not moving much at all. This is the anti-node. It's moving a lot. Next one. Again, the node, I can put my finger here and almost a grand round of applause for his fantastic typing ability.
I don't know why they keep him.
Residence Lab. We need 20 minutes to do this. We got lots of time. Pretty much you're going to follow these directions and then show me your results at the end.